All right, let's do a few examples of integration by parts. Let me just give you the formula again, just to have it here. It's the integral of u dv is u times v minus the integral of v du, right? So that's the formula. And the idea is to try to identify, if we have some weird integral, try to identify a u and a dv. Some dv has to be something we can integrate and transform it so that hopefully we get an easier integral. So, some simple examples you can do, like the examples we did in the first video, are stuff like the integral of x cosine x, integral of x sine x, integral of x e to the x. Each of these, you let u equal x and dv is the rest. And then you just apply this formula. Let me give us just another example. There's some very classic examples here. What if we had something like the integral of x to the fifth ln of x dx? X to the fifth times the natural log of x. Well, okay, so the question is, what's u and what's dv, right? So you can try different things. Like maybe you want to try u as x to the fifth and dv is ln x dx. There's usually two choices you can make. So try, see if I can write the word try. Try to write the word try. Try u equals x to the fifth, dv equals ln x dx. Okay, so then we're going to differentiate x to the fifth, and we're going to need to anti-differentiate ln. So there's an immediate problem there because I don't know off the top of my head the antiderivative of natural log. Remember, the derivative of natural log is 1 over x, but antiderivative, I don't know it. So the idea here is that you need to make a choice in such a way that u is something you can differentiate and dv is something you can anti-differentiate. So no. So better, let's switch them. Let's let u be x to the fifth. I almost said the exact same thing. U is natural log of x, and dv is x to the fifth dx. Okay, and then you can write, what I like to do is I like to just write beneath it what du and v are, right? Du is 1 over x dx. Don't forget your dx, you got to put that in. And then v is 1/6 x to the sixth, right? And you might be worried that looks more complicated than x to the fifth. We actually went up a power, which seems bad, but if we're gonna end up writing down vdu, and you can sort of tell looking at this that vdu is going to be nice. It's going to be nicer, right? Because there's no natural log in it anymore. Okay, so we can just write this out. Then the integral of x to the fifth times ln of x dx. Well, it's u times v, right? I'm using the formula up here. And so we've written down what u and v are, and then I'm going to do minus the integral of v du. So, okay, so that's u times v, which is, well, I'm going to put fine, I'll just write it like the way the formula says. Ln of x times 1/6 x to the sixth minus the integral of v du. V is 1/6 x to the sixth, and du is 1 over x dx. Okay, so nice things start happening here, right? Like we have an x to the sixth times a 1 over x, so there's an x that's going to cancel. So this will cancel with this and make that a fifth power. The 1/6 I can pull out of the integral. This I'll probably put in front just to make it look a little nicer. So we end up getting 1/6 x to the sixth times ln of x minus 1/6 the integral of x to the fifth dx. And that's really progress, right? Because this is an easier integral. This is a much, much easier integral. So in fact, having a 1 over x in here was much nicer, especially with some stuff to cancel it. So that is going to just equal, let me just make a point of that. This is easier. That's exciting. Okay, so when we finish this off, we get 1/6 x to the 6th times ln x minus 1/6. We have to differentiate x to the 5th. We get another 1/6 x to the 6th plus c. And so the final answer is 1/6 x to the 6 ln x minus, well, we have a 6 times 6, which is 36. 1 over 36 x to the 6 plus c. If you want, you could factor out an x to the 6th, you know, I mean, this is a perfectly good answer, but maybe, I don't know, if you were looking for critical points of this function, or I don't know, you know, you might want to factor out x to the 6th. You could even factor out a 1/6 if you want. I guess you could do something like, you know, these are just kind of, you might try different things just to make it look nicer in different ways. That's not, the x is no longer there. So it's something like that. So anyways, this first answer is fine. Okay, so that's one example. So again, I guess the point I wanted to make is that you can sort of try both ways. You know, try this being u and this being dv, or I guess this is u and this is dv. Doesn't really work. So try this as u and try this other part as dv. And that seemed to work better. All right. Another nice example, it's a similar example, it's kind of a famous example. As I mentioned, we didn't really know how to integrate the natural log. So this is kind of funny because we need u to be ln x. We already saw that having dv be ln x is bad because we don't know how to integrate it. In fact, that's the whole point of this problem right here, is to integrate it. And it will sound a little nicer. So we really don't have much of a choice. We make u ln x, so du is 1 over x dx. And then what's dv? Well, dv is what's left over. So if this is u, then in fact dv is just dx. Again, you can't drop the dx's anywhere because of things like this. And when and then that really just means v is x, right? If v is x, then the derivative is just 1, which is like 1 dx. Okay, so that equals u times v, which I'll just write x times ln x, minus the integral of v du. And again, this is nice. We get 1 over x times an x. So we get, yeah, x times 1 over x dx. X's cancel. And we get minus the integral of 1, which is just another x. So we get x times ln x minus x plus c. Okay. So that's actually, there is an antiderivative for natural log of x. It's x ln x minus x. You should always check, right? Check this by differentiating. Pause the video, check it yourself. See that you actually get ln x back. Okay, let me give you another example. Just sort of a classic type of example. We saw t e to the t and all the way at the top here, or sorry, x e to the x. I was saying these work, right? These are kind of simple classic examples. What if there was a higher power of x here? So let me do an example down here of, let's do the integral of t cubed e to the 2t dt. Okay, so definitely a product of different type of functions. We have a sort of a polynomial, a power function here and an exponential function here. So it stands to reason that we'd want to use integration by parts, because that's what we use when we have products of different types of functions. And here, let's see, we want to make a simpler integral. We know that when we differentiate or integrate e to the 2t, we're just going to get an e to the 2t back just with some constants. So if we integrated t cubed, we would get t to the 4th, which is sort of more complicated. If we differentiate it, we'll get t squared, which is a little better. T squared is a little better than t cubed. So let's let u equal t cubed. dv then is the rest. That's the e to the 2t dt. And then we can calculate du, right? That's 3t squared dt. That's from differentiating. And then we can integrate dv. And remember how this works. We get 1/2 e to the 2t. There's no d's in it anymore. Right, this is the antiderivative of that. Okay, so we get, let's just see if this is progress. T cubed times 1/2 e to the 2t, that's u times v, minus v du. So that's 1/2 e to the 2t times 3t squared dt. Okay, to clean this up a little bit, let me just rewrite this as 1/2 t cubed e to the 2t minus, there's a 1/2 and a 3, so I can pull out, so I can get 3/2 t squared e to the 2t. Now, what's the progress we've made? We've gone from a t cubed to a t squared. That is progress. You know, t cubed to t squared is progress, but we're not done. We have to keep going. So this is what's called a repeated integration by parts, because what we can sort of see is that we can knock a power off the t cubed to t squared. If we do something similar, we can make the t squared to a t. And if we do something similar to that, we can make the t to a constant, to a 1, I guess. And then we'll get something we can integrate. So this is a multi-step, multi-stage multi-step integration by parts. And then you got to keep track of all these constants and stuff kind of carefully. So what I'm going to do is I'm going to actually give this a name. Something I like to do sometimes. I'm just going to call this integral I up here, the original integral. And I'm going to call this integral down here. Oops, let's call this I1 or something like that. Okay, so, and because that's the next without the 3/2, so I'm just going to say, so that's the integral we want to evaluate next. But let me just write that formula. We have I is 1/2 t cubed e to the 2t minus 3/2 I1. So if we can figure out what I1 is, we can plug back in. So let's just keep going. So I1 is the integral of t squared e to the 2t. And then we do integration by parts again. So u is t squared. dv is e to the 2t dt. du, we differentiate, we get 2t dt. v, we anti-differentiate, we get 1/2 e to the 2t dt. By the way, notice that one thing that can kind of happen to students sometimes is that you actually switch and you make this u and this dv, and you actually go backwards. You actually get back to where you started, because you're sort of swapping the roles of u and v here. And so this is your u and this is your dv, and then you go back up to here and you get back where you started. So that can happen. That's a pitfall to watch out for. If you just think about hewing down the powers, we're chopping down the powers of t. So, and notice now our du does have a t in it instead of a t squared. So this equals t squared times 1/2 e to the 2t. Oh, I messed up. There shouldn't be a dt here. There's no d's anymore because it's not a d of something, right? This was dv, so this had a dt in it. And when I anti-differentiate, v should just have no dt. Okay. So minus the integral of v du. So minus the integral of 1/2 e to the 2t dt. No. 1/2 e to the 2t times 2t dt. Again, let's clean this stuff up a little bit. This is 1/2 t squared e to the 2t minus, let's see, the 1/2 and the 1 cancel, and the 1/2 and the 2 cancel. And so we actually just get minus the integral of t e to the 2t. Okay, so that's more progress. But this is going to take 3 steps before, because we still can't get rid of, we still need to get rid of this t right here before we can actually anti-differentiate. If this t wasn't here, we could anti-differentiate. Fine. Okay, so let me call this one I2. Let's call this integral I2. So we have I1 is 1/2 t squared e to the 2t minus I2. Again, I'm just recording these so that I can plug them back in up the chain. Once I know I2, I can plug that back in to get I1 and then plug the result in here to get the integral I, right? Okay, so I2, a little bit tedious. You might even pause and try to get ahead of me and see if you can get it yourself, and then check your work against mine. So U is t, dv is e to the 2t dt. du now is just dt, right? We differentiate t, we get 1. And v is, again, 1/2 e to the 2t. Keeps happening that way. And then, okay, so then we get uv, which is these two multiplied together. I'm going to start just being confident we can throw stuff around a little bit. So that's 1/2 t e to the 2t, right? I'm just multiplying these 3 things together. Doesn't really matter what order I do it in. I just like to put the fractions in front. Then minus the integral of v du. But now we just have 1/2 e to the 2t dt. And you can think of the 1/2 pulling out of this integral if you'd like. And then we integrate e to the 2t and we get another 1/2 e to the 2t. And so I think this is going to be, well, let me just copy the previous term, 1/2 t e to the 2t minus, likely it's going to be 1/4 e to the 2t. And there's sort of a plus c floating around, but again, I'm just going to put it in at the end. Right, but when we integrate this, we pop out another 1/2, and that combines with that 1/2 to give us 1/4. That's where I'm getting that. Okay, so we have an expression for I2. This is I2 right here. And then it's just the accounting problem of plugging back in carefully. So then I1, just copying from above, it's 1/2 t squared e to the 2t minus I2. Let me put that in parentheses to be careful because we don't need to distribute the minus sign. Okay, and right, so when we distribute this minus sign, we'll get a minus there, but we'll get a plus here. So I1 is 1/2 t squared e to the 2t minus 1/2 t e to the 2t plus 1/4 e to the 2t. And then we can plug this in. Here, let me put a little box around this. And then we can plug this in all the way back up in this formula here, right? And then we'll get I. So I is 1/2 t cubed e to the 2t minus 3/2. Can't forget about that 3/2 right there. So let me try to be careful. It's almost easier on paper. So then I was 1/2 t cubed e to the 2t minus 3/2. And then we're going to plug in this expression for I2, right? Let me just double check that. Yeah, I'm looking at this. Yep, okay. Or plug in the expression for I1. I might have just said I2, but I meant to say I1. So we're going to plug in this expression right here. Okay, there's the 1/2 t squared e to the 2t minus 1/2 t e to the 2t plus 1/4 e to the 2t. I guess I can throw the plus c in here now because we've got back to the original integral. And then again, I'm just going to distribute this minus 3/2 throughout all the terms. And you do get this sort of nice alternating pattern. So then thus, let me just write this again. The integral of t cubed e to the 2t. That was our original. That was I. That was our original I. That is what this is. Equals 1/2 t cubed e to the 2t minus 3/2 times 1/2. That's 3/4. 3/4 t squared e to the 2t minus minus. So we get plus, and then 3/2 times 1/2 is 3/4. So we get plus 3/4 t e to the 2t, and then minus, and then 3/2 times 1/4 is 3/8. So minus 3/8 e to the 2t plus c. And there you go. Multi-stage integration by parts. It works. Again, check. I know you don't want to, but it kind of works out nicely if you check this. If you differentiate, you're going to need to use the product rule on each of these. But you're going to somehow get a t squared when you differentiate this, and that's going to somehow cancel out that. And there's a 2. Anyways, so then you get some stuff that cancels and ends up working. Okay. So that's a few examples. I'll do one more example in another video just to show you like a kind of a weird example, but those are kind of some of the main types of examples you run into. So I will stop there.